At CECO-Environmental, we're proud to be your single source for pollution control. It's our mission to protect our shared environment, and we relentlessly pursue that goal by providing reliable products and services to tackle your environmental challenges. Purchasing pollution control equipment can be a complicated process, particularly when you have a system that requires many different pieces of equipment. However, our vast range of technologies and solutions for pollution control and product recovery can eliminate that complexity, lowering your total cost of ownership without sacrificing performance. Across a wide variety of industries, CECO helps ensure you achieve real results. No matter your need, CECO has you covered. Simplify your environmental initiatives with our CECO-Environmental family of industrial solutions brands. CECO-Environmental is a global leader in air quality and fluid handling, serving the energy, industrial, and other niche markets. Through innovative technology and application expertise, CECO helps you grow your business with safe, clean, and more efficient solutions that help protect our shared environment. We work tirelessly to improve air quality, optimize the energy value chain, and provide custom-engineered solutions for applications including oil and gas, power generation, water and wastewater, battery production, polysilicon fabrication, chemical and petrochemical processing, and more. To learn more, visit CECOEnviro.com today.
Welcome, and thank you for joining us today for the CECO Certified Continuing Education Series. Today, we will be learning about pumps and thermal fluid systems presented by CECO-Environmental. My name is Mary Rusnak, and I'm the Marketing Manager for the Industrial Air and Fluid Solutions segment of CECO. And with me today is Brian Schnelzer, Global Product Development Manager. While we wait for everyone to join, I'd like to go over some basic housekeeping items about our webinar platform and also the PDH certification. So looking at the slide here, if you have some sound issues, make sure that you check your media player. Make sure that you're not mute. Also take a look at the help widget. That can help you out as well and give you some pointers on what could be wrong. And then finally, you can also log out and log back in. Just use the link from the email when you first joined. At the bottom of your screen are multiple application engagement tools, or what I like to call widgets, that you can use. All the widgets are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A widget. To keep ourselves on track, all the questions are going to be held until the end of the presentation, but you can submit your questions at any time. And if we don't get to your questions, don't worry about it. We get to everybody, even if it's after the event. A copy of today's slide deck and additional help materials are available at the resource list. We encourage you to download any resources or links that you might find useful. If you take a look there, you'll see there's links to our LinkedIn, Facebook, and YouTube page. We post all of our events on LinkedIn and Facebook. That way you can keep track of us if you'd like to follow. The pumps summary would be a useful reference for anyone who is taking the PDH quiz for the PE certification. Hint, hint. Professional Development Hour, or PDH, state information is also listed. Right now, we are able to offer credits in 36 states. Again, if you hover over the widgets on the bottom, they will tell you exactly what they are. So you can share via social, email us direct. The check mark will take you to CECOcertified.com, where you can sign up for additional events or find the on-demand archive version of all of our previous events. We have 2 more events this year: Thermal Oxidizer Basics on October 28th, and then Industrial Ventilation Design on November 18th. And then finally, for everyone, for the PE credits, the 2 last widgets are going to be the ones you're going to want to look at the end, the test and tracker widget. The tracker widget will show you how far along you are in terms of completing items that are necessary, and then the test widget is where you're going to take your quiz here at the end. So just a little bit again, webinars are really bandwidth intensive, so make sure you close out all your other browser tabs. This is going to help make this work better for you. If you notice that your slides are behind, push F5 on your keyboard and this will refresh the page. Chrome also seems to be the best browser for this platform. You can also find additional answers and common technical issues and problems in the help widget at the bottom. An on-demand version of the webcast will be available after the event and can be accessed using the same audience link that was sent to you earlier. So just go back to that same registration link, it'll take you there. All the interactivity will remain in the on-demand version, including testing capabilities. So just to go over today, our webinar value is 1 professional development hour. You need to be present for at least 50 minutes. You need to complete and pass the test, which is basically getting 8 out of 10. When you're done, you want to go to that tracker widget and the certification widget, and there will be a box there that will let you print out your certificate. If you ever need to, you can always come back to the on-demand version and print it out there as well. We suggest that you keep a record log of all the events that you attend, and CECO is going to keep records for 6 years. If you have any questions, just feel free to email me, mrusnak, MRUSNAK@oneseco.com with questions, and there's a widget down the bottom. That's the email that will come directly to me as well. This webinar is 1 hour long, but we will keep the platform open for an additional 30 minutes after the event to allow people to complete the quiz and print out any of the additional materials that they need. So here's the outline for today's presentation. We're going to do a little bit in terms of a basic overview, talk about components, operation, what is high temperature, and then we're going to go into a lot of different items as well as some examples at the end, which I think that everyone will find pretty interesting to see these in actual applications. But before we get to that, before we get to the presentation, we are going to start with our first poll question. So you're going to be able to answer the question here in the next slide. So just hold off for a second here. So how much experience do you have with pump selection? Are you a pro? Are you a little bit of experience? Do you have some experience, or are you what in the world is a pump? And here's where you can place your answer, and I'll give you a couple seconds. All right, let's see what you guys have answered so far. See the results? That's an interesting split. We have 33% an expert with some experience and some with little experience, so that's very interesting. Good. All right, well, I'm going to pass this on to Brian now, who's going to get into the meat of the presentation.
Thank you, Mary. I appreciate it. Good afternoon, everyone. Hope everybody can hear me well. Today's presentation, I'd like to start off with just to remind everyone a few pump basics, how centrifugal pumps work, and then I'd like to get into how these basic machines, common machines, I should say, work in high temperature applications, and what changes with the selection and the design and the overall performance of the pump in when the temperatures start to get high. And just to be clear, when I talk about high temperatures, that's a very general term, I know, but when I talk about high temperatures, generally I'm talking about above 300 degrees F and below 850 degrees F, which would be 150 degrees C to about 450 degrees C. That spans the most common range of high temperature applications. Most pumps are made for below 300 actually, and there are certainly pumps that are made for above 850. But that range will satisfy most applications, industrial applications that are out there. Of course, by definition, a pump is any device used to move or raise a liquid using suction or pressure. That can mean a whole lot of different things. There are many different varieties of pump, from positive displacement, gear pumps, reciprocating pumps, centrifugal pumps, which is what we'll be discussing today. Pressure-powered pumps, there are a wide variety for a wide variety of different industries. Today we're going to focus on the centrifugal pump, and we'll go over some basics, and then we'll be talking specifically about high temperatures and centrifugal pumps. So some of the markets that you see high temperature applications in: oil and gas, lumber, building products, engineered lumber, biofuels, where they're from ethylene production to biodiesel production. We have food processing, rendering chickens, frying potato chips, things of that nature. Asphalt and construction, and also general chemical applications and general chemical production. The centrifugal pump basically uses rotating energy supplied by a motor to spin an impeller. The vanes of this impeller transfer the rotational energy to the fluid as velocity and pressure. The fluid is pulled into the center of the impeller and flung out to the sides, hence centrifugal force. The diagram basically shows the path that the fluid follows through the impeller of the pump. It enters through the center, the rotating impeller, then the vanes of that impeller impart a pressure onto the fluid, and the fluid is then expelled out the periphery of the impeller. That periphery is usually what we call a volute, and it's basically a diffuser that will raise the pressure of the fluid as it rotates around the casing of the pump. Then, of course, it is expelled out to do whatever purpose the pump is meant to do, whether it's just to move fluid from one spot to another, to move it through a process, what have you. The most common use, of course, is just basically raising the pressure of or raising a fluid from one level to another. In this simple diagram, we have a water located in a sump. The centrifugal pump will draw the water from the sump, at which point it will impart its rotational energy into it, raising that fluid up to the overhead water tank. It's basically just a energy transfer machine, taking relatively low energy fluid located in the sump and adding energy via the rotating motor, and it's overcoming the effects of gravity and friction located in the piping and fitting. In discussing centrifugal pumps, we talk about pressure and head. Pressure is a common term, whereas in the pump industry we tend to talk about head. And head is basically what we use to state how much pressure pressure that a pump is actually generating through the machine. As stated earlier, the pump is just designed to add energy and overcome the external forces. The pump does this by generating a differential pressure within the system. The fluid will always flow from high pressure to low pressure. We commonly express pressure, such as in PSI or Newton per square meter, that sort of thing. So it's usually a force acting upon an area. But in the pump world, we tend to express it in pressure in terms of the feet of liquid column. So it would be, or meters of liquid column, and generally we use water as a baseline. Makes it convenient to predict how the pump will operate, moving different fluids and different densities from one point to another. In the diagram that you see above, the liquid basically is pumping to a different height, but the pressure itself, 50 psi in this case, remains the same. So the height difference, and this is all due to the change in density of the fluid itself. As you can see, the equation below is basically the equation that converts head to pressure. So if you have the pressure in the equation, but underneath you have the specific gravity of the fluid. So as the density changes of that fluid, the actual head will also change in the system. Like I said, we normally use water as a baseline. As a manufacturer, we use water as a baseline. But with that, you can then predict how, say, a lighter fluid such as gasoline or a heavier fluid such as caustic or something like that will react with your pump in your system. Conversely, the same is true for pumping. We can pump to the same height, and you will notice that the actual pressure that is recorded on your gauges will be different. In the diagram below, you see that you're pumping to 115.5 feet, and that remains constant throughout. But the pressure, because the specific gravity is changing from 1.2 to 0.7, the pressure in the lines and the pressure that you will read on your gauge will actually be significantly different. In the first case, 60 psi, 50 psi, and 35 psi, respectively. And then it is all, centrifugal pumps are basically defined by a pump curve. Unlike a positive displacement pump, which will basically put out the same amount of flow regardless of the amount of energy you put in. The centrifugal pump works as a velocity machine, if you will. So that it will, the flow rate that will be produced is dictated by the amount of system pressure that it is pumping into. So the flow rate changes with the amount of system pressure, back pressure on the system. On the left of the curve, if the system pressure is higher than where the curve meets the y-axis, the shutoff, no flow condition will exist. As the system pressure lowers, then we start to generate a flow rate of the pump, and to the right side, and as the application point travels throughout the curve, the system pressure will then dictate where on the curve that pump will actually operate. So we've covered, like I said, it's just a few basics of how a centrifugal pump works. From the poll question before, I would guess that most everybody are familiar with the workings of a centrifugal pump, and also the how a pump curve works and that sort of thing. But what I'd specifically like to get into today is how this all translates to high temperature fluid applications. Basically above 300 degrees F, 150 degrees C. Several aspects of the applications must be taken into consideration. First, the properties of the fluid changes as the temperatures increase, specifically the density, which affects the specific gravity, and the viscosity, which affects the fluid resistance to movement. Stationary and rotating portions of the pump will expand and contract due to the temperature changes within. So the pump has to be, these considerations have to be taken in during the design phase of the pump itself, that this pump is going to expand and contract and still remain, still do its job, and the rotating portions cannot be contacting the stationary portions while this happens. The system itself, so what the pump is attached to, will also expand and contract with the changing temperatures. The pump itself acts as a pressure vessel when properly designed, and can handle the full range of the temperatures. The mechanical seal, however, is generally not designed to handle the full range of pressures and temperatures. So that's the last consideration. Now I'm gonna talk about each of these items individually, and how it affects the overall performance of the pump, and how it affects the design of the pump, and how we look at it and consider it in the application. The first is power requirements, and this goes back to the changing properties of the fluid itself. Newtonian fluids, the density of the fluid will decrease as the temperature of the fluid increases. It lowers the specific gravity of the fluid. As you can see, the equation on the right, the power required on a centrifugal pump is the flow rate times the amount of head times the specific gravity over the efficiency of the pump itself. Because the specific gravity is in this equation, that means that the power required for this pump will change as the density of the fluid changes. So that means that it will change as the temperature of that fluid changes. Moving on, we have viscosity of the fluid also affects the power requirements. Viscosity is the resistance of the fluid to move. Basically, the shear forces within the fluid itself build, and as the fluid gets thicker, more viscous, it becomes more difficult to move through the pump and the piping itself, thus requiring more power to move during when it's highly viscous, and less power when the fluid thins out. Once again, for Newtonian fluids, as the viscosity decreases as the temperature increases. So theoretically, as the temperature gets higher, you should require less power to actually move the fluid through. And in most cases that is the case. Let me switch slides here. So for typical operating conditions, we have a typical pump, a 3, 4, 8.5 pump. We want 400 GPM at 200 feet ahead. We're spinning at 3,600. We have our impeller diameter. The fluid is a thermodynamic fluid. Let's say a paratherm NF in this case. And the temperature that it's running at is 650 degrees. The specific gravity of that paratherm is 0.66 at that temperature. The viscosity is 0.3, very, very thin fluid, and very, very light. Those are your operation conditions. So when the engineer goes in and he looks at his conditions and he's going to select his pump and he's going to select his pump and he's going to select his motor and everything else and all the switch gear that go along with that, this is his application and this is what he's going to look at. And for this application, if you examine the curve, the operating power to run this pump is going to be about 18.8 horsepower. And if you go to non-overloading power, which is basically the power at the end of the curve, you get about 23.8. So if you had a 25 horsepower motor on this application, you should be able to cover the operating conditions without a problem. But the problem comes in is that you're not starting this pump at operating conditions. At some point, this pump is going to be at ambient conditions. At some point, you have to start it up. There are some processes that are preheated, but those are not very common, and usually they require the pump to be operating in order to be preheated. So so you have to consider, how am I going to start this pump, and what are the conditions when I do? At startup conditions, we have all the same. The pump itself has not changed, of course. It's still the same size pump. We're still spinning at 3,600. The impeller diameter is still 7 1/4, and the fluid hasn't changed. But the temperature has now changed to 75 degrees F. At that temperature, that paratherm NF has a specific gravity of 0.88, much heavier than the 0.662, and a viscosity of 27 centipoise, significantly different than the 0.66 and the 0.3 centipoise that was at the operating conditions. Plot this same condition on a curve, and the operating power suddenly jumps to 28.3 horsepower. The non-overloading power jumps to almost 35.6 horsepower. This being the case, your 25 horsepower motor that you had spec'd out to cover your operating conditions will probably blow all the fuses and all the circuit breakers in your switchgear to start the pump up. It will overload before it ever gets up to temperature. So in this case, one always has to be aware of the changing fluid conditions at the different application points. You can't consider just your operating point. You also have to remember that this pump has to be started somehow, and it is going to be at an ambient condition when it does.
All right, thanks, Brian. And let's pause for a second here for our next poll question. And just like the last time, you'll be able to put your answers in the next slide here. So what type of pumps are you using the most in your industry? And for this one, you can choose as many as apply. So so crazy here. So we have A, centrifugal pumps, gear pumps for B, diaphragm pumps for C, and then axial pumps for D. And here's where you can place your answers, and we'll give you all a little bit of time to pick and choose the ones that make the most sense for you. Okay, a couple more seconds for everyone to get their answers in, and we'll take a look at the results. Well, I guess it's not really surprising that, most are centrifugal pumps, so at 97%, so everyone seems to have worked with that. And then different varieties in terms of the gear pump at about 19% and 28% for diaphragm, and not maybe as much in the axial, only about 3% there. I'll pass this back on to Brian.
All right, I'm back. It's good to see everybody is 97% on the centrifugal pump side. That's good to see. The next topic is basically thermal expansion, the temperature changes within the components of the pump itself. So as the fluid increases in temperature, this of course is going to transfer to the metallic components of the pump itself, and everything in that pump that is subjected to that temperature is going to be expanding and contracting with that with the changing temperature of the fluid. So simplistically, the pump is a high-speed rotating shaft and a wheel housed in a stationary casing. Of course, the high-speed rotating components cannot touch the stationary components. The pump will not operate very well. That would be problematic. Properly designed high-temperature pumps, they need to take these thermal displacements into consideration. The tolerance and dimensional stack up within the pump must remain tight in certain areas, such as wear rings, to prevent recirculation and efficiency loss within the pumps. But then others, the other considerations, you need to be, the other designs provide a case where the thermal displacements are not eliminated, but their effects, in essence, are negated. So that's the different design aspects of the pump itself that we can include in that basically negate the thermal displacements that the pump makes. For most cases, just a couple examples here. The typical stress-proof steel, which is what is used in a lot of high-temperature shafting and that sort of thing, will grow nearly 1/8 of an inch in length at 850 degrees F. Of course, that's given that most tolerances within a pump are half thousandths to 10,000ths. That can be somewhat problematic. You'll end up running the rotating portions into the stationary portions of the pump, and unless those thermal expansions, thermal displacements are taken into consideration during the design process, and either that or they need to be negated. For an ANSI pump made of a ductile iron, the angle of the shaft will be 0.0158 at 500 degrees due to the vertical expansion of the casing itself. So it's actually bending the shaft. It's causing the shaft to deflect. Same pump manufactured in 316 stainless will deflect the shaft nearly 23 thousandths at 500 degrees. Once again, due to the vertical expansion of the casing itself. A steel shaft will transmit about 662 BTUs from the casing to the bearing frame every hour. And this presents a problem because now you're heating up the bearings and you're heating up the oil and the lubrication aspects of the pump. So all these things need to be taken into consideration when you're actually designing the pump itself. And the different ways that we can negate these effects. For instance, for a pump casing, most ANSI pumps that you see out there, and most pumps are, have a foot mounting, at least for horizontal end cover pumps. The foot mounting, of course, as temperatures increase, the casing of the pump will expand, and all things expand from their base. So in the case of this pump, it's sitting on a base plate. It's sitting on a foundation of some sort. As this pump increases in temperature, the pump on the left, as it increases in temperature, the height of that flange is going to move upwards. Also, the center line will move up along with it. We're trying to keep the shaft and the impeller spinning in the center of that pump. If the center line of the casing is changing, then I'm either bending the shaft or I am at risk of contacting the rotating area with the stationary portion of the pump. So in this case, this is one of the reasons why ANSI pumps and foot-mounted pumps are generally lower, rated lower temperature-wise than other, say, API-type pumps and other process pumps. Centerline mounting, however, when you look at the casing, the actual design of the casing is not any different. It's just where that casing actually is contacting the foundation. Of course, these centerline pads, as you can see, basically looking like ears on the pump itself. Those will be sitting on pedestals that they are then attached to the foundation or the base plate. In this case, as the temperature increases at a pump such as this, the center line of the pump will stay the same because it is at the base of the pump. The pump is going to grow from its base, which is now at the center line. So the bottom half of the pump will grow downwards. The upper half of the pump will expand upwards. But the center line of the pump will stay exactly where it's supposed to be. And thus keeping the impeller, the shaft, and all the high-speed rotating components located right where they're supposed to be in the center of the pump. Another effect is external effects on the pump itself. The external effects, it's not only the pump that is increasing in temperature. Everything is increasing in temperature. As you heat up your system, your piping, your valves, all your fittings, everything else is increasing in temperature. In most cases, these are all insulated items, so they're holding on to that temperature for even after the system is shut down. Once again, at some point, this pump has to be the piping itself and was not installed at high temperature. It was installed at ambient temperature. The pump was installed at ambient temperature. And so these loads and strains, once that piping starts to actually increase in temperature and heat up, it can cause tremendous expansions and contractions depending upon how long the piping is and how many twists and turns it has to make before it actually gets to the pump itself. So the nozzles of the pump must be made to withstand a certain level of pipe loading, a certain level of stress imparted to the pump from the piping itself. A simple way of imagining this is I'm sure, you know, back in college, for those of us that took mechanics and materials, we were all asked to solve this. It's kind of a classic problem where you have a bar of a certain material. It's wedged in between two stationary walls. In this case, the bar is then heated. The question was always, you know, what is the stress then that is generated within that rod? Because now I'm preventing that rod from expanding because I've wedged it in between two walls. And back then, if you remember the formula back then, it was a simple problem, but it was always, at least to me, it always had very surprising results. Because even a small temperature change within that rod would produce huge forces on the walls itself, within the rod itself. As it turns out, this, like I said, this is a rather simple problem back in college, but it can apply directly to the problem of pipe strain and nozzle loading out in the field. As you can see, and this is just an example that I put together. This is actually a case that I had come across. We had if you see the picture in the slide, that's actually a flange, suction flange that has been completely destroyed. It was a iron flange, and the flange was subjected to such a load that it basically snapped the flange in two. When we started looking at it, it was a 6-inch pipe about 20 feet long, 240 inches. It was heated from 68 degrees, which it was just an ambient term. We considered ambient temperature at the time, to about 600 degrees F. The expansion for steel is 6.7 times 10 to the 4th inches per inches degree F, and the modulus of elasticity for steel in this case was 29 times 10 to the 6th, as always. So for an unrestricted pipe, the expansion of that pipe, if you do the math there, you find out that the 20 feet of pipe actually grows 0.855 inches when heated from 68 to 600 degrees F. So if you then take, if you look back at this problem and look at it and then realize, then restrict that pipe, the stress in that pipe, if you restrict that expansion, the stress in that pipe goes over 100,000 pounds PSI. It's just a tremendous amount of force that is generated in the restricted pipe. given the cross-sectional area of the pipe, it can be, we can then, resolve it down to a point force of nearly 500,000 pounds of force that can be exerted on the end of the restricted pipe. Now, of course, the pipe will not remain restricted. It will break bolts. It will break flanges. As you can see, it will bend and twist the pipe, the pump, the piping. It will do everything it can not to be restricted. It's going to move no matter what you try to do. So the way to do it is to mitigate that movement, and the way that's done is basically to use expansion joints, flexible couplings. You can see in this photo here on the lower right-hand side of the picture, that's just a standard centrifugal pump, but at the suction and discharge have both flexible members that keep those forces, moments, and loads separate from the pump itself. Keeps the piping from expanding, gives room for that pipe to expand, and allows the piping to move while keeping the pump stationary without putting exceptional loads onto the nozzles of the pump. Now, of course, the pump is designed to withstand some piping loads. It has to be. But it is the piping designer or the end user that is responsible to keep those loads under the maximum given by the manufacturer of the pump. Those loads can, as you can see, those loads can be tremendous, and they can be coming in many different directions from from each axis and moments around those axes, bending moments and whatnot, and all those have to be taken into consideration when installing the pump. The flexible members are a very good way of keeping those loads to a minimum. It does not eliminate them altogether, but it will keep those loads to a minimum, and will allow the piping to expand and contract without necessarily affecting the pump in any major way.
All right, thank you.
All right.
And we are getting to our last poll question here. So this one, again, answers on the next slide. What type of fluids are common in your industry? So something as basic as water, hydrocarbons, and oil, or chemicals like caustics and acids? And put your answers here, and we'll give you a second here to answer, and we'll take a look at the results. All right, let's see what everyone is using. Okay, that was an easy one. So 100% water out there. Okay, good to know.
Wow. All right, that was actually surprising, those results. Mostly water, the hydrocarbons and oil. I gotta admit that most of the applications that I do are for hydrocarbons and oil. Water is a particularly tricky substance. Once it's a great substance to pump as long as the temperatures stay low. But once water gets above 250, 300 degrees, it becomes a very difficult liquid to pump. the pressures get tremendous, the vapor pressure of water. You must keep it at a very high pressure in order to keep it in a liquid state. And it also loses all of its lubricating properties that water is known for. It wants to flash into steam at a moment's notice, and so it becomes a very difficult fluid to work with at higher temperatures. Hydrocarbons.
Yeah, it looks like the slide actually updated a little bit, so maybe I clicked too fast here because now we have a little bit different results. So
no, it's fine. Hydrocarbons and oil is with has its own problems. Often the vapor pressure and of the oil causes a lot of vaporization and whatnot. So it's good to see that there's a good mix of applications out there. So on to the last segment of the high temperature world of pumps. Is protecting the seal. Protecting the seal in the pump. The typical pressure and temperature limitations on a pump made for high temperature applications are approximately 500 psi at 750 degrees F, maybe that's about 35 bar at 400 degrees C. This limitation is made to maintain proper operation. The actual structure of the pump components can withstand much higher conditions. Safety factors for the pump pressure vessels generally run anywhere from 1.5 to 3 times the design conditions. So there's generally not a whole lot of worry about the pump failing due to high temperature, or the pressure vessel, the pump failing due to high temperature or pressure. What is problematic, however, is the seal that is used to seal these pumps is not designed to handle those incredibly high temperatures and pressures. Oftentimes, it does tend to be the weak link in the pressure temperature chain, the seal is, of course, composed of a rotating and a stationary portion. It incorporates thin wall bellows, oftentimes elastomeric seals, O-rings, gaskets, things of that nature. The protecting the seal in the high temperature applications, it becomes a priority. So oftentimes the pump is built around the seal in order to protect it and protect it from the high temperature, high pressure atmosphere. Down at the bottom, I give just a quick diagram of, on the right side is the basics of how a seal works. The seal basically breaks down high pressure through a very tight tolerance of very flat faces, one rotating, one stationary, of course. And within that cross section, it breaks down the pressure until it cannot flow. There's no differential pressure to release it from the pump. You can, however, get vapors and whatnot that come through the seal. So it's not a perfect seal, I guess, is the way it should be explained. It's never a perfect seal. On the left-hand side, I just kind of pinpoint some of the different nomenclature used in describing a seal and whatnot. In order to protect that seal, for years we used external methods to protect those seals, and still do today. Those methods, they started out using cooling water, that basically use the cooling water to as an external water source coming in. So this had nothing to do with the pumpage, nothing to do with what you were pumping. You would pump these cooling water through jackets that surround the seal chamber, basically cooling that seal chamber down, cooling the seal down, regardless of what temperature you were pumping up in the business end of the pump itself, where the impeller and casing are. So it was cooling just a localized area of the pump. The problem with water cooling is just that. I mean, now I've used this water to cool this pump down. I've taken the heat from the pump, I put it into the water. Now I have hot water coming out the other end. What do I do with it? Big companies such as, the Exxons, Dows, DuPonts of the world, they have cooling towers and they have effluent ponds that they can take this water and process it and cool it down. But not everybody has that sort of ability. And oftentimes the water was allowed to just travel down the drain. Oftentimes you were pumping anywhere from a half gallon to 4 gallons a minute through the pump, depending upon the temperature that you wanted to bring the seal down to. With that in mind, it was incredibly wasteful. It was expensive. Water is a precious resource, as most of us know. Depending upon where you are in the world, it may not be available, such as desert applications, that sort of thing. Now we still do use water-cooled pumps today, but they've been taken over by air cooling for the most part in high-temperature applications. Air cooling, as you can see as the diagram on the right-hand side, air cooling uses the ambient air to cool the pump down. It's certainly a preferred method. The air is free and plentiful, and for this design, what's taken the seal has moved from right behind the impeller, and they've moved it all the way to the back of the pump. At which point we're using a fan to force convection across the bearing frame, pulling the heat out of the metal, pulling the heat out of the fluid itself. And in most cases, the temperature can, if you're pumping 650 degrees at the casing itself, we can lower the temperature to less than 180 degrees at the seal. And that's just through forced air convection across the bearing frame itself. As you can well imagine, the industry took to this with open arms. No more water, no more piping, no more dealing with hot water afterwards, no more paying for the resource. So in this case, you can see an air-cooled pump. The top picture is basically the pump operating in visible light. The pump is spinning away, doing its thing. And then we took that same pump and took an infrared thermal image of the pump itself. And that's located in the lower photograph there. And you can see the white areas are actually 400 degrees F. Whereas as the temperature goes back, you can see that it drops pretty drastically as it approaches where the seal actually is. The seal location is kept at less than 140 degrees, and all this is due to basically a battle between conduction and convection. The conduction of the fluid and the metal components of the pump, they wants to push that temperature down back to where the seal is, whereas the forced air is pushing convection back and keeping that conduction at bay, basically. And the temperature gradient between the two, as you can see, is nearly 300 degrees, and that's approximately 11 inches of actual distance between those 2 points. Another way that we protect the seal is through flushing systems. And these are often, most of these systems were developed by API, the American Petroleum Institute. And these systems use they basically use a circulating fluid that does a number of different things. Flushing the seal is a common way to keep fresh fluid around the seal. It's a common way to keep solids from building up at the seal faces, and it's a common way of getting more reliability and longevity out of the seal. But that fluid, that flush fluid, in high temperature applications can also be cooled. It can also be filtered in some cases. In two most common flush loops, we would call an API Plan 21, which where the flush is circulated due to differential pressures within the pump. So on a Plan 21, we would take, and you can kind of see it in the lower right-hand picture. We take a stream of the pumpage off of the discharge of the pump, which is obviously the high pressure area of the pump. That stream then goes back to a small heat exchanger that is cooled either using that heat exchanger. It can be a water to liquid heat exchanger, or it could also be an air to liquid heat exchanger, depending upon how you want to set it up. But that flush fluid goes back to the heat exchanger, gets cooled, and then basically gets injected back into the seal phases. With that in mind, it's always pushing that fluid through, and the differential pressure between the discharge of the pump and the seal chamber is always going to be. There's always going to be a differential enough that you're going to continue to get a significant amount of flow. Typical flush flow rates are anywhere from a quarter GPM to maybe 1 GPM. So the flush fluid rates are generally very, very low. Another method is called Plan 23.
Brian, I'm going to
yes.
Brian, I'm going to interrupt you here for a second. We're actually kind of at the end of our presentation. Have gone long here, so I'm going to interrupt for just a second here. And for anyone, we want to be respectful of your time. If you are not able to stay here, Brian's going to try and wrap it up maybe in another 2 to 3 minutes here quickly. But, you know, if you're not able to stay, totally understand. For anyone who needs the certificates, just remember the last 2 widgets are where you are going to need to find your information. That's where you're going to take your quiz. And when you have fulfilled all the requirements, that's also where you'll be able to print. We unfortunately won't have time to get to any questions live, but we will reach out to every one of you who had a question and get back to you. And again, just anyone, if you can't stay on, we understand, but want to thank you for coming. And Brian, if you think you might be able to kind of breeze through some of these here in the next 2 to 3 minutes, that would be awesome.
I will. I won't be able to talk about the applications, but I'll be able to wrap this up really quickly. So going back to the flush systems. So basically, the next shows that Plan 21 in action. You can see that it's coming off of the discharge, going through the heat exchanger, and then down into the seal chamber. At the heat exchanger, the flush is cooled, and it is injected back into the at the seal chamber, keeping that seal much cooler than the actual pumpage itself. I'd also like to thank AES Seal for these animations. They're excellent animations, and they're a very good seal company, and we do appreciate them allowing us to use these. This is the Plan 23, and you can see that we're using a pumping ring to basically force that fluid. We're not taking that fluid from the hot pump, from the hot discharge. Instead, we're just recirculating the fluid that's already in the seal chamber. So you can see that through a pumping ring, we raise the pressure and put it into the heat exchanger, cool it down, and then re-inject it back into the seal chamber. The Plan 23 method is by far the preferred method in most cases because it's much more efficient. You use less cooling water, you use less, you lose less BTUs out of your system to cooling the seal. This is basically done through a phenomenon called a heat soak. The high temperature conducted through the pump and shaft. So there's all sorts of things going on in the seal chamber itself. You have conduction from the pump itself, the metal components of the pump. Low temperature fluid entering the pump from the heat exchanger. Fluid lowering the temperature of the seal chamber through convection and the circulation of the fluid itself, and then higher temperature fluid that's then exiting that seal chamber. So it's a rather complex heat exchange question, but API 682 has a rather rudimentary, very simplistic calculation for trying to figure that out and to see how many BTUs you're actually going to require to keep your seal chamber at a certain temperature. We generally like to keep the seals under 350 degrees. That seems to be where they operate best, at the most reliable, and give you the best performance and longevity. So if we're operating at 650 degrees, we want to bring that seal temperature down to 350 degrees. So the heat exchanger is going to be required to drop 300 degrees. The next is a modified method that was developed that's much more accurate, much more. It also takes in all the different considerations that go into this rather complex heat exchange problem, heat transfer problem. And those include the speed. The seal is actually generating heat. There's a number of different aspects of the pump that are taken into consideration with this equation. I won't go through all these different items. You guys can take a look at that, and it's rather plain to see that all these coefficients take up a different aspect of that heat transfer problem. And just a few quick items. This is a typical high temperature heater skid that you can see. This is a heater unit with that is used to increase the temperature of hot oil, and then that oil goes off into your process to do whatever it needs to do. The pump in this case is a 468.5. It's an air-cooled max temperature of about 650 degrees. This is a high-pressure boiler return, the unit itself is operating about 20,000 pounds per hour. The pump is a 1.5 3, 8.5 with an air-cooled 400 degrees max. Here's a gas dehydration skid. They use triethylene glycol to dehydrate gas streams. The glycol is has a great affinity for water. The triethylene glycol is injected through the gas stream. Pulls out the water. Then the mixture is then put into a boiler. The water is evaporated off or steamed off, and then the triethylene glycol is then just recirculated into the process. And this is also a TEG glycol heating system. And that wraps it up for me. Sorry I went over time, folks. I got a little long-winded there for a moment, so I apologize.
Thank you, Brian. But at least we know everyone got their required 50 minutes in there if they need that PDH. So that's awesome. So again, just want to thank everybody for attending today. We appreciate it. We know your time's valuable. Just to remind you, over in the resources side, there are copies of all the slides as well as a little summary that can help you with some of the questions as well as some other materials. 2 more events that are going to be happening this year, so hope you can make it to them. And if not, we will have them all available on demand at cecocertified.com. Thank you again. Take care.